Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor of chemistry in University of Delhi. Today, we are going to discuss about the module Low Energy Electron Diffraction Study, and we'll talk about the introduction related to this under the paper of Surface Analytical Techniques Part 1. When you complete this module, you will be able to very clearly understand the basic concepts involved in this, the development of LEED technique as a tool for surface chemistry, then the question why do we study this technique LEED, and lastly, what are the advantages and disadvantages of this particular technique. Theory of low energy electron diffraction, which deals with the introductory part of this. Low energy electron diffraction (LEED) is one of the first and one of the most successful surface sciences techniques for structure determination ever invented. For more than 50 years, it has been the dominant method to study the structure and morphology of two-dimensional plane surfaces. From its invention in 1927 by Davidson and Germer until today, a vast variety of very different techniques and extremely sophisticated applications have been developed. For the structural analysis of atomic positions in surface unit cells, LEED 1 to 5th analysis has been developed with an accuracy of less than a few hundred angstroms. Furthermore, for determination of complex surface structures, this has been automated. Besides the intensity of diffraction spots, also the profile and position contain important information about the surface morphology, which can be analyzed by spot profile analysis, that is LEED, or it is called SPA LEED. In the following, both kinematics and dynamics theory of LED will briefly be described, since the spot profile analysis (LEED) analysis is based on kinematic theory, whereas the tensor LED analysis based on the dynamic theory, and both will be used in the present explanation.
Low energy electron diffraction is a technique for determination of the surface structure of single crystalline material by bombardment with collimated beam of low energy electron 20 to 200 electron volt and observation of diffracted electrons as spot on a fluorescent screen. LED may be used in one of two ways: qualitatively, where the diffraction pattern is recorded and analysis of the spot positions give information on the symmetry of the surface structure. In the presence of an adsorbate, the qualitative analysis may reveal information about the size and rotational alignment of the adsorbate unit cell with respect to the substrate unit cell. Quantitatively, where the intensities of diffracted beam are recorded as a function of incident electron beam. Energy to generate the so-called 1 to 5 curve. By comparison with theoretical curve, these may provide accurate information on atomic position on the surface at hand. Basic principle. The basic principle of a standard LEED experiment is very simple. A collimated monoenergetic beam of electrons is directed toward a single crystal surface, and the diffraction pattern of the elastically backscattered electron is recorded using a position sensitive detector. For electrons, like for all wave-like objects, the angular intensity distribution due to the interference of particle wave backscattered from a periodic array is described by Bragg's law, or more conveniently by a set of Liu equations, one for each dimension of periodicity, which predict a regular pattern of diffraction spot. To understand a lot of physical and chemical properties of solid substances, the knowledge of solid structure is very important. It is important for explanation phenomena in heterogeneous catalysis, microelectronic, etc. It exists a lot of method how to determine the surface structure. One of the most popular is LED. In LED, we investigate elastically scattered electrons. Typical energy range in LED is 30 to 500 electron volt. Due to the very strong interaction with matter, electrons have a mean free path in the same order as an interatomic space is. By measuring a diffraction pattern for certain energy of incident electrons, a periodicity of surface lattice may be determined by kinematical approach. One of the main assumptions for kinematical approach is that the incident electrons scatter in the crystal just once. This assumption is often not fulfilled, but the kinematical theory describes the diffraction pattern well. A current in the direction of the diffraction maxima can be measured, and the results of this measuring are the so-called 1 to 5 curve, which means that the spot intensity are measured as the function of the electron energy. For curve interpretation, the dynamical approach is used, where the multiple scattering is taken into account. With this method, we can determine an exact position of atoms, relaxation, adsorption, position, etc. Dynamical approach has a statistical error 0.02 angstrom in the determination of atom position in the direction perpendicular to the surface. The discovery of electron diffraction by Davison and Germer in 1927 and subsequent development in the vacuum technology and solid state physics during the following decades. The low energy electron diffraction LED has become a standard technique in surface science, and Nobel Prize 1937 for C.J. Davison proof that electrons behave like wave together with Germer. Electron energy 30 to 300 electron volt, wavelength around 1 angstrom, and electron penetrate about 10 angstrom into the surface. Elastically scattered electrons are detected at the fluorescent screen, and it allows quantitative determinations of the atomic structure of an ordered solid surface, often down to the first 5 interlayer spacing with an accuracy of a few tenths of an angstrom. Since the late 1960s, when the technique itself and complicated theory required in the interpretation of the electron diffraction data had become established, RHEED has contributed a major part of currently known ordered clean and adsorbate covered surface structures.
Tensor LED approximation. As described above, the theory of dynamical low energy electron diffraction has been well developed since 1970. It allows the reliable calculation of intensities for structures in principle of any complexity. However, though the clean and low indexed surfaces, the calculation can even be performed on a microcomputer, the mini computer. The necessary computing or computer efforts grow considerably with increasing complexity. The scale, depending on the approximations used, with n2 to n3, where n is the number of atoms in the unit cell. Though the calculations could be speeded up by the use of symmetry adapted functions, the angular momentum expansion this remain fatal for the retrieval of the correct values of structure parameters when a scan of the parameter space is used to find the best theory experiment fit in a trial and error procedure. This is because the number of trial structures grows exponentially with the dimensionality of the parameter space, that is, the complexity of the structures. Therefore, the strategy to solve complex structures by LEED must be twofold. On one hand, the computer effort to calculate the intensities for a certain structure have to be reduced. On the other hand, the scan of the parameter space has to be given up in favor of directed search procedure or direct methods. In fact, both strategies were followed during the last decade. The substantial reduction of computer time for the intensity calculation was made possible by the introduction of the perturbation method tensor LED. Of course, any reduction of computer time for the calculation of intensity of a trial structure must use certain approximations instead of applying the full dynamical theory. In the latter, approximations are also used, which, however, can be iterated to yield accuracy, and such approximations have been tried since the early days of LED calculations. All of them consider only a subset of the total of the multiple scattering processes, which is of course at the cost of accuracy. Nevertheless, these approximations or approximate schemes prove to be useful in a number of cases. However, they are made largely superfluous with the development of the powerful tensor LED method. The underlying theory was developed by the London Imperial College group. It marks most important progress in LED theory made during the 1980s, and its essentials are presented in the subsequent portion of this. In this, we have been talking about low energy electron diffraction spectroscopy. In contrast, the LEED characterization is usually done in a separate vacuum chamber that is connected to an epitaxial growth chamber. LEED measurements are particularly useful in determining the surface geometry of the starting substrate used for the interface growth, such as an insulator semiconductor interface. Both RHEED and LEED analysis are also excellent methods to solve detailed surface atomic structures via comparison of angle or electron energy dependent diffraction intensity with the corresponding intensity curves calculated and refined with potential atomic models. While discussing several examples of LEED and RHEED patterns, our goal is to provide the learners with the basic tool to interpret on their own RHEED and LEED data. For an in-depth study of the instrumental and physical concepts, we recommend several excellent books. which one can read to know about this very useful technique. This can also be read or known from some review articles which have been given in different references. Introduction. Low energy electron diffraction (LEED) is one of the most powerful techniques used for surface analysis. It is used to study surface structures, bonding, and the effects of structures on the surface processes in materials. The low energy electron diffraction technique operates by bombarding a beam of electrons from an electron gun to the surface of the sample being tested. This slide deals with the characterization of the several technologically relevant semiconductor surface layer by means of the two surface sensitive measurements: reflection, high energy electron diffraction (RHEED) and low energy electron diffraction (LEED), which visualizes the reciprocal lattice of a surface layer studied under this. RHEED is the standard equipment in the epitaxial growth chamber, providing a great opportunity to monitor surface properties during the growth process. This real-time in situ method makes it possible to control the growth and atomic layer precision. The schematic diagram of this, wherein we take a crystal and from there the energy radiation that passed, we take an electric gun. That electron gun fires on a crystal structure, on a crystal surface, and the rays are reflected and brought back on the screen, which are then analyzed and energy of various orbitals or official states calculated. Here lambda is equal to h upon 2m kinetic energy half for a 20 electron volt electrons, and lambda is 2.7 angstrom. Remember that this is the order of the crystal lattice parameter, which also has been given here.
Sample preparation. The sample is usually prepared outside the vacuum chamber by cutting a slice of around 1 mm in thickness and 1 cm in diameter along the desired crystallographic axis. The correct alignment of the crystal can be achieved with the help of X-ray method and should be within 1 degree of the desired angle. After being mounted in the UHV chamber, the sample is chemically cleaned and patterned. Unwanted surface contaminants are removed by ion sputtering or by chemical process such as oxidation and reduction cycles. The surface is flattened by annealing at high temperatures. Once a clean and well-defined surface is prepared, monolayers can be adsorbed on the surface by exposing it to a gas consisting of desired adsorbate atom or molecules. Often the annealing process will let bulk impurities diffuse to the surface and therefore give rise to a recontamination after each cleaning cycle. The problem is that impurities which adsorb without changing the basic symmetry of the surface cannot easily be identified in the diffraction pattern. Therefore, in many LED experiments, agar electrons spectroscopy is used to accurately determine the purity of the sample. We can to a certain extent control the defect structure and defect density of the layers grown by controlling the lattice mismatch. Three techniques have been mainly used for this purpose. The most simple one make use of the fact that a metal single crystal may be oxidized and a more or less well ordered oxide film is formed. In the case of nickel oxide and cobalt oxide order, thin oxide film can be grown by the oxidation of nickel and cobalt's single crystal surface. The growth of NIO layers on nickel The LED patterns of oxidized nickel surfaces, however, mostly indicates the presence of rather imperfect NiO film on the top of nickel, which might result from the large lattice mismatch of nearly 20% between nickel and nickel oxide. Although the use of highly oriented nickel as substrate lead to considerable improvement of the lead pattern from the oxidized surface, the large lattice mismatch always remains a problem, with the possible consequence of defect structures in the oxide film. And different approach to prepare well-ordered nickel oxide film was used by Mare and Nadermeyer, who evaporated nickel onto a gold-silver surface in an oxygen atmosphere. LED and UV photoelectron spectroscopy have shown that a well-ordered and smooth nickel oxide can indeed be obtained in this way. The reason for this more perfect growth of nickel oxide layer by using a gold substrate is the smaller lattice mismatch between nickel oxide and gold. LED pattern of silicon 100 reconstructed surface. The underlying lattice is a square lattice, while the surface reconstruction has a 2 into 1 periodicity. As discussed in the text, the patterns show that reconstruction exists in symmetrically equivalent domains, which are oriented along different crystallographic axes. The diffraction spots are generated by acceleration of elastically scattered electrons onto a hemispherical fluorescent screen. Also seen is the electron gun, which generates the primary electron beam. It covers up parts of the screen.
Theory of low energy electron diffraction. Low energy electron diffraction, as it is abbreviated as LEED, is one of the first and one of the most successful surface science techniques for structure determination ever invented. For more than 50 years, it has been the dominant method to study the structure and morphology of the two-dimensional plane surfaces. From its invention in 1927 by Davison and Germer until today, a vast variety of very different techniques and extremely sophisticated applications have been developed. For the structure analysis of atomic positions in the surface unit cell, LED can analyze and the methods have been developed with an accuracy of less than a few hundred angstrom, which is extremely accurate result. Furthermore, the determination of a complex surface structures has been automized. Besides the intensities of the diffraction spots, also the profile and positions contain important information about the surface morphology, which can be analyzed by spot profile analysis, that is LEED and SPALEED. That's what is called spot profile analysis, LED. In the following, both the kinematic and dynamic theory of LED will briefly be described, since the SPA LED analysis is based on the kinematic theory, whereas the tensor LED analysis based on the dynamic theory, and both will be used in the incoming slides. LED may be used in one of the two ways: qualitatively, where the diffraction pattern is recorded and analysis of the spot position gives information on the symmetry of the surface structures. Here, in the presence of an adsorbate, the qualitative analysis may reveal information about the size and rotational alignments of the adsorbate unit cell with respect to substrate unit cell. Quantitatively, where the intensities of the diffracted beams are recorded as a function of incident electron beam energy to generate the so-called IV curve, that is current versus potential curve, this can be generated. By comparison, the theoretical curves, these may provide good information on atomic positions on the surface at hand or the surface which is being studied.
Principle of operation: a beam of electron of a well-defined low energy, typically in the range 20 to 400 electron volt, is incident normally on the sample as shown in this figure. The diffracted electrons can be observed on a fluorescent screen after energy filtering grids, which selects only the electrons with the same kinetic energy as the primary electron.
Historical background of this LED. This, as has been conveyed, was invented by Davison and Germer. This discovery of electron diffraction ultimately led to the development of this equipment. The theoretical possibility of the occurrence of electron diffraction first noted in 1924 when Louis de Broglie introduced wave mechanics and proposed the wavelength or wave-like nature of all particles. In his Nobel laureated work, de Broglie described that the wavelength of a particle with linear momentum p is given by h by p, where h is the Planck's constant. The de Broglie hypothesis was confirmed experimentally at Bell Labs in 1927 when Clinton Davison and Lester Germer fired low-energy electrons at a crystalline nickel target and found that the angular dependence of the intensity of backscattered electrons showed diffraction patterns. This was repeated number of times and similar results were obtained. These results were consistent with the diffraction theory for X-ray developed by Bragg and Lowe earlier. Before the acceptance of the de Broglie's hypothesis, this hypothesis diffraction was believed to be an extensive property of waves.
Development of LED as a tool in surface science. Although discovered in 1927, low-energy electron diffraction did not become a popular tool for surface analysis until the early 1960s. We have already discussed about that. The main reasons were that monitoring directions and intensities of diffracted beams was a tough experimental process due to inadequate vacuum techniques and slow detection methods such as Faraday cup. Also, since LEED is a surface sensitive method, it required well-ordered surface structures. It soon became clear that the kinematic single scattering theory, which had been successfully used to explain X-ray diffraction experiments, was inadequate for the quantitative determination of experimental data obtained from LEED. At this stage, a detailed determination of surface structures including adsorption site, bond angle and bond length were not possible.
The advantages and disadvantages of LED have been listed, and these can be studied in detail also. In the determination of surface structures, it is very useful. And second, in the determination of surface chemical bonds, they shall find very good applications which can be very accurately measured when the surface chemical part is considered. The disadvantage of this are not very many, but then major disadvantages are: one, that this cannot detect the surface properties during the process of film growing on the sample surface. That means when the film is being grown in a dynamic conditions, it will be difficult for the surface properties to be measured with the help of the slow electron diffraction technique. These are some of the disadvantages that this technique possesses. So students, I'm sure you would have learned the basics of this technique called LED, and now let us summarize what you have learned in this module. This technique used for surface analysis of the material is very important because it gives results up to a very low atomic level. It is used to study surface structure, bonding, and the effect of the structure on the surface. Bombardment with a collimated beam of low energy electrons, the range is 20 to 200 electron volts, and observations of the diffracted electrons as spots on a fluorescent screen. LED may be used in two ways. Qualitatively, it gives information on the symmetry of the surface structure. In the presence of an adsorbate, it gives the information about the size and the rotational alignments of the adsorbate on unit cell, and also gives the alignment in which the surface is covered. Quantitatively, by comparison with theoretical curves, this may provide good information on atomic position on the surface at hand. The interaction between the solid and the electron is especially strong in case of LED. Upon penetrating the crystal, primary electrons will lose kinetic energy. In inelastic scattering processes, the electronic mean free path depends on the energy. It is independent of the material. The mean free path turns out to be minimal 5 to 10 angstroms in the energy range of low energy electrons, that is 20 to 200 electron volts. LED cannot detect the surface properties during the process of film growing on the sample surface. That means it fails in situ analysis. Thank you very much.